In this video, we're going to look at the mechanism of a Fischer esterification. And the reason this is valuable to do is not to memorize this mechanism, but just to see that we can get it started and we can figure everything out along the way. And that should give us some confidence to be able to attack these types of problems in the future. Let's jump right in. In a Fischer esterification, we start with a carboxylic acid and an alcohol. Let's change the R group, it doesn't matter what they are. We use a catalytic amount of maybe sulfuric acid, and we make an ester. And that's a carbonyl with an oxygen and another carbon on the other side. So, what's the mechanism? How do the electrons move to get us from here to here? So let's think about how we might reason through a problem like this. If I see H plus acid, I'm thinking if I have a positive, I need to find the most negative parts over here that might want to react with a positive. And of course, the most negative spots are these lone pairs of the negative electrons, these juicy negative lone pairs of electrons. So I can find 3 spots with those electrons that might want to react with this H plus. And if you're going to memorize one thing in the Fischer esterification, it's out of these different electrons, these on the carbonyl are the ones that go and grab the H plus. And let's see what that makes. So these other oxygens might grab an H plus later, okay? So we have R, C double bond O, OH, and this oxygen has now a hydrogen on it. So there's a positive on that oxygen. And we still have my alcohol with its lone pairs of electrons. And there's 2 here. So don't forget those. Okay, at this point, we're looking ahead, and we see that this carbon needs this OR group on it. This carbon has this OR group on it. So somehow this oxygen needs to attack this carbon. Now you could, at this point, let these electrons come attack that carbon. That would make too many bonds on that carbon, so we can move these electrons up to the oxygen. That's perfectly reasonable to do. Other people like to draw resonance forms at this point. And I think I'm one of those people. I like to draw resonance forms when I can. Whenever I'm stuck, start drawing resonance forms, and let's see how that helps me get to the final product. So this wants some electrons because it has a positive charge. Where can it get electrons? It can get them from the double bond. So we can move some of these electrons up onto that oxygen. And that would make R, C, single bond O. Now there's 2 lone pairs on that oxygen. And there's still a hydrogen on it. There's this OH on this carbon. And now this carbon only has 3 bonds because one of those went up to the oxygen. So now my positive charge is on that carbon. Resonance forms. So now I start looking at this and saying, okay, now this carbon, once attacked, it has a positive charge. Let's let this oxygen, we know it, this OR needs to get on that carbon. So let these electrons come attack. Notice that just makes sense if I know where I'm going. So that makes a carbon with an R group. There's an OH on this side. There's an OH up here. And now on this carbon I have an O. So one of these lone pairs is there. There's a hydrogen, 1 lone pair of electrons, and R prime from the attacking group, the attacking alcohol. This oxygen doesn't look right. If I think about its formal charge, there's a +1 on that oxygen. So I went from a positive and a neutral overall positive. I still have to have an overall +1 on this one. Okay, now anytime I see something like this, we might remember from SN1 reactions or different reactions that I like to clean this up. So you could take a molecule of alcohol, or there's water in my acid. So let's just pick water. You can pick whichever one. and it's got lone pairs of electrons, and we can clean it up. These electrons can grab the H+, leave those electrons on the oxygen to make. So R to C, I have an OH up here. None of that's changed. This OH hasn't changed. And down here I have an O with 2 lone pairs. This bond is now these 2 electrons. And I have an R prime on there. All right, so let's look at the final product and see how close I'm getting. I have R, carbon, oxygen, R prime. So that part's all there. And the part that needs to be a double bond O is a carbon to this O and to this O. So one of these groups I need to leave. And I evaluate that and I say, what do I think about this OH? Not a very good leaving group. How about this OH? Not a very good leaving group. How can I turn it into a good leaving group? Ah yes, there's acid in here. So you could pick whichever one of these you want. They're the same. But one of these OH groups, let's just pick this one. These electrons could go grab H+, and that makes R, C, O, R prime. This OH I didn't touch. And this O now has an H on it there and an H on it here. 1 lone pair left and a positive charge on there. And we've seen this before in this chapter. That's a great leaving group. So let's let that leaving group leave. And that makes R, C, this OH I haven't touched. This OR I haven't touched. And that water left. So that leaves only 3 bonds on this carbon with a positive on that carbon because these electrons left that carbon and went onto the water. Now that I have this compound, I'm getting very close. Somebody might take the water, pull off that H+, move those electrons down to the double bond all in one step. Perfectly reasonable to do that. I prefer to want to draw resonance forms again. So let's see, this positive charge wants some electrons. This oxygen that I'm trying to turn into a carbonyl says, well, I can give you 2 electrons. So that makes R, C. I'm going to shift this OR up a little bit, OR prime. And now the top of this carbon atom has a double bond to an O with 1 lone pair on it, and a hydrogen, and a positive charge. And I look ahead and boy, that looks close. I'm almost there. Now I just need to pull off this H+ to get me here. So we can clean it up, I like to say, with another molecule of water or alcohol. Take your pick. These electrons could grab this H+. Oh, let's use my blue color I've been using. Those electrons can grab H+. These electrons can stay behind on the oxygen. So let me draw that arrow better. These electrons can stay behind on that oxygen. And that makes my final product. I'm home. So there's what, 6 to 8 steps? I think I used 8 steps because I have resonance forms. Other people may want to do 2 of these steps in one time. That's okay to do. You don't have to draw these resonance forms. So for instance, back here, instead of doing this part, I could have done this. Pulled off the H+ and let these electrons go down to the carbonyl. That would have been okay to do. Or instead of doing this resonance form, I could have let that oxygen attack that carbon and the electrons go up to make my next step. You don't have to do the resonance forms, but I like to. Okay, so bottom line, don't memorize 8 steps of a mechanism. Learn how the mechanism begins. If there's acid, protonate the most negative spot on your molecule. And then just practice enough you gain confidence that you can solve this problem. Attack, clean it up. Attack again, clean it up. Draw resonance forms when you need to. And you can reason your way through until you get to the final product. It looks scary at first, but if you go through this mechanism a couple of times, this is a perfect one to practice on to gain your confidence so you can attack other mechanisms in the future. I hope that helps. Hey, subscribe to my channel, Watch more of my organic chemistry videos, and I'll help you gain confidence that you too can do organic chemistry.